Hello and welcome to this first video in the Determinant Proofs series. I've decided to make a separate playlist for determinant proofs because they are so much more complicated than matrix proofs, and there are a large number of them and they take a long time to explain, and use different concepts like permutations to explain them. So we'll start with this theorem that says that the determinant of a matrix is equal to the determinant of its transpose. So we'll need to prove some other results first, before we can dive into the main part of this proof. We have to prove that this statement is true. A lot of it will get explained before we get into it. We'll have to prove this statement so as to prove the above statement, which is that the parity of a permutation is equal to the parity of the inverse of this permutation. And we also have to prove this, that all of these ordered pairs of numbers can be matched up. It's easier to write this using sets. Then we'll have to prove this statement, which I'll explain later. And then finally we can put it all together to prove this simple statement that's written at the top, and I'll call it Part C. And so now for some definitions. If you're interested in determinant proofs, then you must already have a lot of knowledge of linear algebra. I guess that you'd know about permutations. The set Sn is the set of all permutations with size n. Here's the set of all permutations of size 1, and it's extremely simple. It only contains the identity permutation. There's not a lot that you can do with a set containing only one element. This is the set of permutations of size 2. It contains two elements, the identity that doesn't do anything, and the permutation that swaps the only two elements. And this is the set of permutations with three elements. There's about 6 of them, and there's enough of them to make this set look interesting. The next definition is that of the parity function, which is a measure of whether the number of swaps required to get a permutation back to the identity is odd or even. So it returns -1 if it's odd and 1 if it's even. And it's written like this, with the permutation variable sigma bounded on both sides by straight lines. It looks like the absolute value function for real numbers, but it's the parity function for permutations. I'll just scroll this screen up to make more room. And here's an example of calculating the parity of a permutation. This is the identity, and the number of swaps required to get it back to being the identity is 0, which is an even number, so that it returns 1. And this permutation requires 1 swap to get it back to being the identity, which is an odd number, so it returns a -1. So we'll use this statement in the proof, which is a product of entries in a matrix. We'll use this permutation as an example, and then we'll use this 3x3 matrix. Now to calculate the value of this variable so as to get an idea of what it represents. We'll evaluate what sigma 1 is, which is 2 in this case. Sigma of 1 is 2. And then we'll use this pair of indices to determine the value of this entry in the matrix. It's the first row and second column, so it's 2. Now to calculate a product of matrix entries. We'll calculate the values of sigma from the permutation function above. Then we'll use these indices to find their values in the given matrix and multiply them together. And this is the value of this product. So now to perform a calculation of a determinant, we'll get the determinant of this matrix. This is the formal definition of the determinant. It's equal to this sum. The sigma summation symbol sums up this expression on the right for all of the permutations in the set Sn, that is, all of the permutations of size n. There are only 3 of these entries for each permutation, so we can simplify it immediately. We don't have to write out that sigma is an element of Sn each time we write out the sum. We can simplify it to be just small sigma, and know that we're summing it up over all the permutations of this size, because small sigma is a variable representing permutations. Then we could expand out this sum like this. So these are all of the permutations that it uses. I've decided to set it out like this so that we could see how each permutation contributes to the determinant of this matrix. I want these products to be positive and multiplied by the parity later, so I place them in absolute value bars. I've decided to set any of the entries in the matrix that aren't represented by this permutation to 0, so as to better see all of the individual permutations. We also have to write in the parity of each permutation. They'll be equal to 1 or minus 1. So I'll scroll everything up the screen here. Then I'll fill out the values of all of these parities. Then I'll scroll this page up again. Then I'll evaluate all of these determinants. And it'll be all these numbers added together, which will give us this number, which is equal to the online matrix calculator's answer. So now to prove part A of this theorem, and I hope that you have some idea now of what this all means. We're going to have to make this particular manipulation in our main proof. It looks like we can replace sigma with the inverse of sigma in this line. So in order to prove this result, we have to prove this, that the parity of a permutation is equal to the parity of its inverse. And also that this is true, that these ordered pairs in these sets can be paired up. It's easier to write it in set notation. So now to prove part A1, we'll start with this statement that says that the product of a permutation with its inverse is equal to the identity permutation, which is the definition of an inverse of a permutation. With permutations, function concatenation and multiplication are the same. Then we can get the parity of both sides, which should be equal. If the functions are equal, then their parities must be equal. And evaluating these parities gives us 1, because the parity of the identity permutation is 1. We can also use a theorem from permutations to split this parity up into the product of the parities of two functions. So combining these equations gives us this equation. And since the parity can only be equal to either 1 or minus 1, then we can substitute these numbers in to get this equation, which we were trying to prove. So now to prove part A2, we've got to prove that these sets are equal, so that we can show that these pairs match up. We'll prove that they are equal by showing that these ordered pairs match up. I only used sets because it was a compact way of showing you what I wanted to do. We could rewrite these sets like this, so I hope that you can see that we're trying to prove that these sets need to pair up. Using this sort of set notation with a dummy variable will help us to prove it. So firstly, we'll set the first numbers to be equal for all of the ordered pairs that we're trying to match up, and then we've got to show that the second numbers in the ordered pairs are equal too. We'll do this by applying the inverse of sigma to both sides of the equation. And the inverse pairs cancel to give us I by itself, and so the second numbers are always equal when the first numbers are equal. So all of these numbers match up. We can write it like this as an equality, and show them in the sets where they need to be equal. And so these two sets are equal, so we've proven part A. Now to prove this result, it says that if we replace sigma by inverse sigma in this sum, with sigma as the dummy variable, then these expressions will still be equal. So now to start this proof, we'll set these variables to be equal to these sets. The first set contains all of the permutations of length n, and the next set contains all of the inverses of these sets. And we must prove that these sets are equal, so that the inverse of sigma will span all of the permutations of length n. It suffices to show that no elements in the second list of permutations are equal, and then because both sets have the same length, then they'll be equal. We'll set the inverses of two permutations to be equal, then it must follow on that their root permutations must be equal too. So we'll start with the first permutation we want to prove to be equal, and we can just add an inverse pair to the front. We can use this equality to change the indice of this inverse permutation. We can then swap the brackets, which can be done with permutations. And then we can eliminate this inverse pair, and so get the other permutation. So we've proven these permutations to be equal. So we've proven part B. Now to prove the main part of this proof, which is part C, that the determinant of a matrix is equal to the determinant of the transpose of this matrix. We'll expand out the definition of the determinant. We'll use B for the entries of A transpose. It looks a lot like the expressions that we've already been working with. We can also write it out using this product symbol, which may seem confusing to people who aren't used to it, but it is worth showing, even if it's not required as part of the proof. We can flip these indices and use the entry symbol A directly for the matrix A, so this is the determinant of A transpose in terms of the entries of A. We can then transform this expression into this using part A of this theorem. The products in green are the same because we've proven that the indices are the same but just swapped around, and that these parities are the same. Then we can use part B of this theorem to transform this expression into this. It says that they are equal because the dummy variable sigma covers all the possible permutations of length n in both cases. So we can write as sigma varies over Sn, then so does inverse sigma. And because this is the definition of the determinant of A, we can write out that it's equal to the determinant of A. So that's it. We've proven the whole theorem. So I hope that this video has made sense to you and has therefore been helpful and educational. You might need to watch it a few times to get familiar with it. If you did find it helpful, then please support this channel by clicking like and subscribe. Feel free to write anything helpful in the comments and to share this video. And thanks a lot for watching.